and we're just going to basically fill these notes out. In my opinion, this is probably one of the more difficult things mathematically that we do all year, and as long as you kind of understand and you've been getting the whole concept of equilibrium, it pretty much makes sense, but just knowing what to do when the equilibrium tells you what to do. But again, I think it's one of those more confusing things, especially as we get to parts B and C. So in your notes, we're on Roman numeral 5, and we're basically looking at titrations and calculating the pH during a titration. And we're going to look at 3 scenarios: a strong acid with a strong base, then we're going to get weak acid with strong base, and then strong acid with weak base. Okay? So before any base is added to the acid, and again up here you can kind of see we have 0.1 molar HCl, and we're going to have eventually 0.1 molar NaOH. So before we add any base, so we really just have HCl in our liquid water. So we're going to go ahead and write initially we have 0.1 molar HCl. Our liquid water doesn't matter because it's liquid and we're only concerned about aqueous things. And originally we have 0 hydronium and 0 chloride. And because it's a strong acid, it's going to essentially completely dissociate. So we're going to say all of this dissociates. So our X really equals 0.1. And these are both plus X and plus X. So these become positive 0.1 and positive 0.1. So at equilibrium we have no HCl as a compound together, but we do have 0.1 molar hydronium and we have 0.1 molar chloride. We know that chloride ion, because it's the anion of a strong acid, does not contribute to pH. Okay, it does not hydrolyze or react with water. So really, to get our pH, we are just going to use our pH equation and take the negative log of hydronium. And because we know hydronium is 0.1, we can just substitute that in right there. We find out that our pH is simply 1. Okay, and that's fairly straightforward. Just a Ka really is all you need there. And the Ka is for strong acids are huge, so you don't really need a Ka, you just need the molarity of your strong acid. Alright, so now we're going to add some base before the equivalence point. And the equivalence point is when we've added equal moles of acid and base. So you see in this scenario we have 40 milliliters of 0.1 molar HCl. We have 10 milliliters of 0.1 molar NaOH. So essentially a couple things can happen here, or how we calculate this. We might do 40. I'm just going to put this off to the side. 40 milliliters of HCl, and yeah, we'll make it a little bit bigger. Alright, so we have 40 milliliters of HCl, which probably is much easier to write like this, 0.040 liters. Alright, or kind of another thing that can happen is if we just multiply volume times molarity, we get moles. So if we take that and multiply it by 0.1 molar, we end up getting 4 millimoles. Alright? And we don't really talk about millimoles that often, but that's fine. So we have 0.4, or I'm sorry, yeah, 4, just 4 millimoles. And we're going to divide that then by our entire volume. So notice we're adding 40 milliliters of HCl and 10 milliliters of NaOH. So we're really going to divide that by 50 milliliters. And because we're dividing millimoles by milliliters, we're going to get molarity back. So in this case, we have a molarity of 0.08 molar HCl. And likewise, we're going to have, we're just going to divide our 10 times 0.1 divided by 50, and we're going to have 0.02 molar NaOH. So over here, we're going to put, we have hydronium in water, and it's 0.08 molar, and our hydroxide is 0.02 molar. And again, we have 0 water to begin with. Really, water doesn't matter because it's liquid, but we have 0 sodium chloride to begin with. And the sodium chloride we're not real concerned about because what's true about it? Sodium is the cation of a strong base, chloride is the anion of a strong acid, so this is inert anyways. Alright, so it does not react, it does not hydrolyze, so it doesn't contribute to pH. So in this case, we have 0.8 molars hydronium, 0.2 molars NaOH. OH is going to run out first. Alright, so really our X is just going to be 0.02. So we have 0 OH left, and we have 0.06 moles of hydronium. Water doesn't matter, and HCl doesn't matter. So again, in order to get our pH, we're just going to simply take the pH equals negative log of hydronium, and this time our hydronium is 0.06. Alright, which gives us a pH of 1.22. Alright? So it doesn't change a whole lot as we start adding base. But then at the equivalence point, alright, so we're adding equal volumes of acid and base. We're going to get our initials real quick. And kind of the last time, and I didn't really talk about this specifically, but our initials, we're going to take our molarity of our HCl and divide it by our total volume. Does that really exist? No, because as soon as we start pouring stuff, they're going to start reacting. But again, it gives us a pretty good sense of what our molarity is if we double the volume. Alright? So in this case, we're going to have 40 times 0.1 divided by 80. Alright, so we're just really taking half of 0.1. So we really have 0.05 molar HCl, and we have 0.05 molar NaOH. Water doesn't matter, and sodium is inert again, sodium chloride. So these are going to run out at the same time. So our X really is 0.05, 0.05, this is 0, this is 0. Again, these don't matter. But because we have pure water, what is our pH going to be? It's going to have a pH of 7, because we have equal parts hydronium, equal parts hydroxide. And then after the equivalence point, alright, so notice we still have our original 40 milliliters of HCl, but now we've gone past the equivalence point and added 20 extra milliliters of NaOH. So in this case, we're going to have 40 times 0.1 divided by 100. So this is going to end up being 0.04 molar hydronium. And then we're going to have 60 times 0.1 divided by 100 is going to be 0.06 molar hydroxide. And again, our water doesn't really matter, NaCl doesn't matter, but this time our acid is going to run out first, okay? Because it got completely neutralized by our base, and we have extra base. So acid's gone, and our base is 0.02. Alright, so a couple ways we could do this. pH plus POH equals 14, and then POH is simply negative log of hydronium. Alright, so that's the way I would probably do it. So negative log of 0.02 ends up being 1.22, kind of like our last one. Or no, it was 0.6. So what is 0.02 going to be? It is really going to be, we're past our halfway point, which is the 0.03, so it's going to be 1.7. Alright, but we're going to subtract that, because 14, or really x, we have plus 1.7 equals 14. So x must equal 12.30. So that is our pH. Okay? So these ones are fairly straightforward. This is not the difficult stuff, but that's kind of how titrations work if we're having a strong acid or strong base. So our next stuff is going to be a weak acid plus a strong base. And notice we are having sodium hydroxide as our strong base. Oops, you're not seeing that. Sodium hydroxide is our strong base, and HF is our weak acid. So again, if we look at, let's see, before any base is added, so we have 0.1 molar HF. Water doesn't matter. We have no hydronium, no fluoride. And this is not going to completely dissociate, so it's going to be minus x. We're going to have plus x and plus x. And then at equilibrium, we're going to have 0.1 minus x. We're going to have x and x. And then Ka of any acid is going to be really H concentration times our fluoride concentration, all divided by HF. Again, water is not part of this because it's a pure liquid. So now if we just substitute these numbers into our equation, we're going to have x times x, and we're going to assume that this x is small, like we've been doing since equilibrium. So really we're just going to divide by 0.1, and all this is going to be equal to our Ka for HF, which is 7.1 times 10 to the negative fourth. So we're going to multiply this and then take the square root of it, and we find that x equals 8.43 times 10 to the negative third. Alright? And because x is hydronium, if we take the negative log of that, we can get our pH. So pH in this case equals negative log of that. So pH equals, let me see what my notes are, 2.07. Alright? So again, notice we have the same volume as we had of HCl, but before we add anything, because HCl is a strong acid, its pH is much lower. Alright, so again we're going to add some base before the equivalence point. We have 40 milliliters of HF and 20 milliliters of 0.1 molar NaOH. So we're going to take 40 times 0.1 and divide it by 60 this time. And we find that our HF to begin with is 0.067, and our OH to begin with is going to be 0.033. Our water doesn't matter, and our F now is going to be 0, and it's going to play a part because it's no longer chloride, which is the anion of a strong acid, but it's fluoride, which is the anion of a weak acid. So it does hydrolyze. We're going to see what that means in a second. So in this case, our it's before the equivalence point, so OH is going to run out first, which makes sense because we have its concentration is less, or its moles are less. So that is the amount that's going to run out, and HF is going to be negative 0.033, or positive 0.033. And then when we work this out, we get 0 base, and this becomes 0.034, and this becomes 0.33. And really, in all actuality, and this is 0.06666 repeating, this is 0.03333 repeating, it's really 0.033, and this is really 0.033 as well. Okay? But long and short of it is, even if it wasn't, our Ka expression, if we look at it again, is hydrogen ion times fluoride ion all over hydrogen fluoride, or hydrofluoric acid. And we have a couple values now. Our H plus we don't know. Alright, it is not in our balanced equation over here. So it is going to be our X. And really we're going to put our 0.033 in for our F minus. That's going to be divided by really 0.033 down here, even though we have written 0.034, just because of rounding. And we're going to set that equal to 7.1 times 10 to the negative fourth. Alright, because that is our Ka for HF. So notice these cancel, and X simply equals 7.1 times 10 to the negative fourth. So if we take the negative log of that, that gives us pH, and we find that our pH equals 3.15. You can see that this change is quite a bit higher than our last change, although our last change, I forgot, I only added 10 milliliters instead of 20. Alright, so our next thing is going to be at our equivalence point. Again, we have 40, we're going to divide it by 80, so we're going to have 0.05 to begin with, and we're going to have 0.05 to begin with, and water doesn't matter, and 0 fluoride. So what is going to happen with our HF and our OH? It is going to completely run out, both of these. HF and HF. We make this much water, but our water doesn't matter. And we also have this. Right, so we have 0 HF, 0 hydroxide, and we have 0.05 fluoride ion. Okay? If we try to put this into our Ka, though, it doesn't quite work, because again, if we look at this, we would like to get our H plus concentration, because that helps us get pH. We have F minus, but we don't have HF now. Alright? So because of that, what's going to happen is, if we have fluoride ion really floating around in the midst of water, it hydrolyzes. So the following reaction is going to take place. F is going to react with water to form HF and hydroxide ion. Okay? So if this is true, we know we're beginning with 0.05 molar F minus. Water doesn't matter. We have 0 HF and 0 OH. This is going to change negative X. Alright? This is going to change positive X and positive X. So at equilibrium, we have X molars of hydroxide. We have X of HF. We have 0.05 minus X of our F minus. Okay? So this equation then, because this is now written as a base, alright, because F is the conjugate base of HF, we really need to find out what our Kb value is for HF. Alright, and Kb is simply equal to Kw divided by Ka. Or we're going to set this 1 times 10 to the negative 14th divided by 7.1 times 10 to the negative 4th. And we find out that Kb equals 8.3 or it equals 1.4, my bad, times 10 to the negative 11th. Okay? And then our Kb expression for this would simply be Kb equals HF times hydroxide, which also can help us get pH, all divided by F minus. Alright, and now we have a couple of these numbers, right? Because we have HF and OH are both X, so X times X, and then F minus is 0.05 minus X, and again, all this equals 1.4 times 10 to the negative 11th. Again, we're going to assume X is small, so this is going to go away. So really we have X squared over 0.05 equals 1.4 times 10 to the negative 11th. And as we solve for X, we find that X equals 8.3 times 10 to the negative 7th. Alright? And again, X is our concentration of hydroxide. So again, don't forget that. So if we take the negative pH of this, it's going to give us POH. So we find that POH equals 6.07, which leads us to conclude that pH equals 7.93. Okay? So notice at the equivalence point now, our pH is not 7, but it is higher than 7, alright? Because our strong base is kind of winning the battle, but it's overcoming our weak acid. And then after our equivalence point, we get back to a fairly easy one. And again, this is the most difficult. At the equivalence point is where you have to pay attention. To titrations. After the equivalence point, however, so we're going to start off with this again. So we're going to have 0.04 molar. We're going to have 0.06 molar. Water doesn't matter. HF kind of does, but we're going to see that it doesn't in a second. So our HF runs out. So we're going to run out of acid first. Positive F. So we have 0 HF. We have positive 0.02 moles of OH. And then we have positive 0.04 moles of F minus. From here, we could again work out the hydrolysis of F minus, and it's going to be a very minute number compared to just the hydroxide we're finding out right here. Okay, so now we're simply going to say POH equals negative log of OH concentration, and we know our OH concentration is 0.02, negative log of 0.02. And 0.02 is 1.7. We're going to subtract that from 14 and find that our pH is 12.3. Okay? So after equivalence point, we're going to disregard the hydrolysis of this because its value is going to be very small compared to 0.02. We'll get a value probably somewhere in the neighborhood of what we got up here, of 8.3 times 10 to the negative 7th, okay, which is negligible compared to the 0.02 molar OH we have of just leftover strong base. Alright, so similar things for this next little section. Weak base plus strong acid. Now our weak base is going to be ammonia, and our strong acid is going to be HCl. So before any base is added, our NaOH, we have 0.1 molar NaOH. We have no water, water doesn't matter. Our OH, we have 0. Ammonium, we have 0. This is a weak base, so it's not going to completely dissociate, so it's going to come apart just X. Positive X, positive X. Over here we're going to do 0.1 minus X. We have X and X. So again, Kb equals, in this case, OH minus times ammonium, all divided by ammonia. Alright, and that leads us to X times X, or just X squared, all over 0.1 minus X. We're going to assume this is small compared to 0.1, so we're going to get rid of that, and we're setting it equal now to 1.8 times 10 to the negative 5th. Alright, so we're going to multiply by 0.1, take the square root of it, and we're going to find that X equals 1.34 times 10 to the negative 3rd. Alright, and again, this is now our OH concentration. So we're going to take negative log of this and subtract it from 14. So our POH comes out to be 2.87, and our pH is 11.13. Okay, which makes sense because we have weak base with no acid in it yet. Alright, so our next one is going to be before the equivalence point. So it's going to be similar to number 2 on our last example. So we have 40 of this and 20 of this, so it's going to be the same kind of type thing, 0.06. Let's do 666, repeating. Hydronium, we have 0.033, repeating. Water, is it HSO on your handout? It should be H2O on your handout, doesn't matter. And ammonia is the cation of a weak base, so it does hydrolyze, so it will play in. So our hydronium runs out, but that's how much it's going to change, 0.033. We're going to get an equal molarity of ammonia. So at the equilibrium, we have 0.033 molar ammonium, we have no acid, we have 0.033 molar ammonia. So get KB of ammonia. What it looks like is, if we have ammonia in water, we're going to make ammonium and hydroxide. So we're really going to have hydroxide ion times ammonium ion all over ammonia ion, which is what we did just above. So in this case, OH helps us determine our pH. It's going to still be X. We're going to multiply that 0.033. We're going to divide it by 0.033. So notice these cancel kind of like the last time. And again, we're going to set this equal to 1.8 times 10 to the negative fifth. So these cancel, so X equals that. So if we take the negative log of that, we get POH, which equals, in this case, 2.8. No, that's what was last time. It equals 4.74, which means our pH is going to be 9.26. Okay? So our next one is at equivalence, and this is our more difficult one. So our ammonia, we have 40 milliliters of both, so we're just going to cut our molarities in half. So we really have 0.05 ammonia to start with. We have 0.05 acid to start with. Water doesn't matter, and we have 0 ammonium. Our ammonia is going to run out. So is our strong acid, right? And we're going to produce 0.05 molar ammonia. So at equilibrium we have 0, 0, water doesn't matter, and 0.05. And just like above, our KB now does us no good, okay? But what do we have floating around? We really have ammonium floating around. And it's in the presence of a lot of water, alright, because we've just made more water by our neutralization. So if we react this, we really form ammonia back with hydronium ion. Okay? So now that we're forming hydronium, we really need a Ka expression. And again, we can always get our Ka expression from our Kb expression, because Ka equals Kw divided by Kb. So in this case, it's going to be 1.0 times 10 to the negative 14th divided by 1.8 times 10 to the negative 5th. We're going to find that our Ka is 5.6 times 10 to the negative 4th. Okay? So here's our expression. Where NH4, we have 0.05 molar. Water doesn't matter. We have no ammonium to start with. We have no strong acid to start with. This is going to change X. Positive X, positive X. So at equilibrium, we have X moles of acid, we have X moles of ammonia, and we have 0.05 minus X moles of ammonium. Alright, so we're going to set 5.6 times 10 to the negative 10th equals X times X, all divided by 0.05 minus X. X is small, so we're going to get rid of it. So really we're going to multiply, take the square root of both sides, and we find that X equals 5.29 times 10 to the negative 6th. Alright, and this now is our hydronium concentration. So if we just take negative log of that, we find that our pH is going to equal 5.28. Alright? And then our last one is going to be acid after equivalence point, and it's going to be just as easy as base after equivalence point. We have 40 and 60, so we're just going to divide stuff by 10. So we have 0.04 molar ammonia, and we have 0.06 molar acid. Water doesn't matter. Ammonia, we start with 0. Our ammonia is going to run out. before our acid does. So that's 0.04 plus 0.04. And at equilibrium, we find we have 0 ammonia. We have 0.02 moles of strong acid and 0.04 moles of the conjugate acid, I guess. This molarity is going to be weak compared to the strong acid. So we're really just going to take the negative log of hydrogen concentration, which is 0.02 in this case. So our pH equals 1.70. Alright? The very last thing is, what do titration curves look like? Alright, so what we're going to do is we're going to draw 4 titration curves. This is what I want you to put at the bottom of your notes, just in this space, works just fine. Alright, pH is our y-axis, and really the only pH we're really concerned about is a pH of 7, which should be right in the middle. So 7, 7, 7, 7. If we have strong acid plus strong base, our pH curve is going to start flat at the bottom, and it's going to go up really quickly, and it's going to be flat at the top. Okay? And the equivalence point should be right smack dab at 7. Okay? If we have, I think we'll just go in order, a weak acid with a strong base, what happens is our weak acid, instead of being flat like this, it's going to have a little curly Q, kind of like that, and it's going to go up, and it's going to flatten out, and our equivalence point is going to be somewhere above 7. Alright, so notice this was right on line with 7, and now this is somewhere above 7. If we have a strong acid with a weak base, our titration curve is going to start flat, right, and it's going to go up, it's going to kind of flatten out and have a little curly Q up here. And our equivalence point is going to be somewhere below 7. Alright? But a great factor to look at in looking at these is a weak acid always will start with kind of a curly Q type, something like that. And then here's our strong acid plus weak base. And then the last one I want you to have is if we have a polyprotic strong acid. So something like maybe H2SO4 with a strong base. And this one is going to start flat. It's going to have a pH, it's going to level off. It's going to have another curve and level off a second time. Alright, why does it have 2 equivalence points? Or not really equivalence points. Why does it have 2 plateaus? Because it is diprotic. Okay? And a triprotic acid, something like phosphoric acid, would have 3 separate peaks. Okay? So anyways, that is it for the notes. Like I said, I think it's the most difficult thing we do all year is that equivalence point pH calculation for titrations.